Hey, good afternoon or good morning. What time is it? I think it's still morning. Yeah, good morning. Yeah, it's morning. Yesterday we did prove something, but we left a lot of loopholes to fill in because what we did yesterday is more like intuition driven approach. Okay, and now it's time for us to add some mathematical. Okay, now we're going to take some formalist approach. Okay, so which uh, we cut a lot of corners. Okay, so uh, kind of like jumping through the hoops. We cut a lot of corners, and so it's time to scrutinize what we did yesterday. Okay. Yeah. Instead of just me looking at that, let's look at it together. How about that? Uh, yeah, yesterday midnight express karaoke session, some martial arts. Right. Time to get back to work. Uh, Gold bus congestion, we'll get to it, okay? But I'm just not ready to get back to it. Why? Because uh, there's a little bit of progress that I want to share with you at some point, okay? But let's do this. Why? Because we are really having fun with this. Okay, so can we do this? Can we go from here to there? Can we distribute this union guy? Let's think about it. I mean, let me grab some water. Okay, so yeah, think about it. Can we go from here to there? That's a little bit, you know. Let's think about that. Okay. Okay. Smoker's cough. All right. So nothing to worry about. Yeah, I talked to my family in Korea yesterday, and yeah, they're doing great. Yeah, they're doing fantastic. But I don't know this shelter in place. I mean, me, I go to work, but I've been always shelter in place. Okay, except going to work and shopping in the Walmart. Other than that, I've been doing this for years. Humanology series. Okay, by now, like I guess 2 years. All right, so the yeah. Yeah, we can do this. Why? Because it's by definition, if you have a set, No. Would this work? Yes. Why? Because you're adding a constant to a set, right? And union 1 over 2, union 1 over 2, union 1 over 2, that's just 1 over 2 because it's constant, right? So, and also a constant plus a set by definition is distributive, right? Yeah, it does work. Okay. Yeah. Mm-hmm. It's a beautiful proof, okay? It's a really beautiful proof. I really liked it. Yeah, it was very beautiful proof. It was really beautiful proof. Yeah. Now, let's prove this. Alpha plus 1 is alpha. Okay? Let's formally prove that. Intuitively, we know. Okay? Shifting window, number density doesn't change, right? But we need to formally prove this thing. Alpha plus 1 is alpha. Okay? We need whiteboard, right? Okay. Let's grab the guy over there. Yeah. Okay. Oh boy. Okay. So I'll do without alcohol as far as I can. Okay, and then I start drinking later. If you think I'm going too fast, I'm sorry, but I cannot slow down any further. Why? Because we got a lot of things to do. We're busy. Okay. Uh, if you're lost, just go back, rewind, and look at again. Okay. The previous whiteboards. Okay. Yeah. Then you get it. Okay. All right. Alpha plus 1 is equal to alpha. Let's prove it. Left hand, right hand. Okay, so so we start with definition. Okay, proof. Proof. Uh, all right. Uh, there. We go. Okay. We start with definition. Okay, so alpha is equal to cardinality of natural number. All right. Now, alpha plus 1 and in when no number is positive, uh, absolute value is distributive. Okay, so you can kind of factor it. Okay, it's the opposite direction of distribution. We are distributing from here to there this function absolute value. Okay, and we are factoring it. Make sense? Because one is absolute value of one, right? Okay. Well, n is union I from. Okay. Okay. Let's give you some example. Okay, so you have zero. You know what? We'll start with one. Okay, but it doesn't matter. All right. So now plus one. Okay, so n plus one is always distributive. Okay, set addition. We want to prove that absolute value of this one, two, three cardinality, okay, is equal to absolute value of two, three, four. Can we prove this? I mean, it's intuitively true. Like shifting window, same number density, right? But to prove this, I'm not sure if we should accept this as an axiom or is it provable? You have to identify the very bottom rock, okay? The rock bottom, bedrock, okay? And this could be it, one of those axioms that we cannot quite prove. Or not, I don't know. Yeah. Let's think about this. Oh boy. Uh, so what we know is this, okay? Absolute value of n plus 1 is same as absolute value of n, okay? And because they are positive numbers, it distributes, so that's why we have okay, so alpha plus 1 is equal to alpha. But is then can we subtract alpha and 1 becomes 0? Can we subtract alpha? I guess not, huh? Yeah. It's like alpha minus alpha 0. Can we do this? Meaning alpha times 0 is equal to 0. Can we do this? Meaning, equivalently, is 0 0 over alpha interesting question. We know 1 over alpha is not 0, okay? Why? Because it's infinitesimal, it's going 0, the limit of that is, yes, 0, where it's going, okay? Target. But it's not never equal to 0. Why? Because it's still ongoing. Alpha is infinite, alright? So, we cannot do this, alright? Alpha minus alpha is not 0. Okay, why? Because the way we define alpha is this. For example, here you have alpha, I mean n, and here you have n plus 1. They're two different sets. But alpha is the number of elements in there. Yeah, it is infinite, I know. Okay, but by definition, it's unit of infinity, standard infinity. Okay? Let's take a break. Yeah. How interesting. Very philosophical mathematics, right? Yeah. That's why it's very interesting. Okay. Let's take 5 minutes. Yeah. It's quite windy outside. So, uh, so we defined the cardinality of a infinite set as in conjunction with number density. Okay, if a given fixed window of counting, don't freak out. Okay, just wanted to tilt it up. That's all. Okay, so number density. Okay, so yeah, intuitively number density doesn't change when you add number to an infinite set. So I mean, let's talk about finite set. Let's talk about finite set. All right. Let's talk about finite set. All right. Let's step back a little. I want a drink. All right. So with your indulgence. All right. Okay. I want horseshoe mushroom drink. And okay. Um. Let's see. Where's my horseshoe mushroom? Both of them? Oh wow. I don't know. I have two of them. How interesting. To make sure you didn't go bad. Okay. Oh well. I guess that's just fine. Okay. So, he says one and two. Okay. Let's be minimalist. And absolute value of this guy plus one is equal to absolute value of, let's distribute, right? 2 comma 3. Okay, good. Now, can we distribute this absolute value? I guess not. Why? If we distribute that, then what? 2 plus 1, 3. But isn't that kind of what we did down there in our proof? I Yes, we did, but the situation is different because we are dealing with down there when we prove something that we are kind of questioning now, scrutinizing. We are dealing with the infinite set. Okay, so the situation is a little bit different. Okay, but when you deal with finite set, you cannot quite distribute this absolute value. Okay, so all right, very good. But so it's good to know that. Good, but so that this distribution of function, the group theory is abstract algebra. I think they kind of deal with that kind of linearity, something like that. I don't know. Yeah, abstract algebra is really cool stuff. Okay, it's in my list of things that I'd like to learn at some point. Like group theory, that stuff. Okay, but I don't have time. All right, so if time allows, yeah, I'd like to learn those things. Okay, maybe after I retire or something. Even if I retire, I'll be writing books. Okay, I probably won't be learning. Maybe if I get really bored. Okay. Good vodka. Now, okay. So, what we have learned is this. When you add a constant singleton to a set, the number of that set does not change. Why? Because you are adding one to each of these members, but it's not a union. Okay, it's plus. Okay. Um, you're adding number to each member. All right. So that's why the number does not change. Okay. Uh, we are kind of I'm kind of confused because we've been too lax. All right. Um, alpha plus one. That's a little bit too much shortcut there. Okay, because I yeah, we took too many shortcuts. Okay, let's give it some mathematical rigor. All right. Okay. Okay. If a proposition is true for finite set, is that proposition also true for infinite set? That's a good question to ask, right? If so, we have a hypothesis, okay? If a proposition regarding what is proposition? It's a function, okay? So Boolean function. If a proposition Boolean function is true for finite sets, when the input of this Boolean function is a finite set, then is that when the proposition is a Boolean function, propositional function, when its input is infinite set, is it always true? What I'm saying is, if some Boolean function, okay, of when its input is some finite set, okay. If this is true and when its input is infinite set, is this also true? Okay, so that's the hypothesis. It's the proposition itself. Okay, this entire thing is some propositional function that takes two inputs. Okay, f and I. Yeah, we are being very abstract. Okay, so yeah. Which is not difficult. Okay. Okay. All right. If we can do this with the finite set, can we also do this in the infinite set? Okay, so that's the question we are asking. How interesting. Whew. Ah, boy. Mm. Yeah, I'm struggling a little bit. Okay. Oh boy. Hmm. Okay. Yeah. Let's study some additive set theory. Okay. What I'm saying is, I'm not going to look up any Wikipedia or anything, just because we deal with some finite sets. Okay, and then we come back to infinite set. Why? Because we need to understand some more about additive set theory. Okay, so I'm not going to look up Wikipedia or anything. We'll just work it out some examples. All right, like what's the cardinality when you add two sets of different lengths, like set of two members and set of three members. What becomes of cardinality? Okay, so I'm kind of curious. Okay, all right, let's take a break because I'm kind of wondering. So you cannot quite distribute absolute value. Okay, my guess is that when you add two sets, three sets, whatever, my guess is the resulting set becomes its cardinality is the maximum card of those cardinalities. Okay, that would be my guess. Let's see. Okay, all right, very good. Oh boy, yeah. Let me take off these long pants. It's kind of getting hot. Uh, okay. We need to grab another whiteboard. So, okay. All right. I'm sure I wrote this down. So, additive set theory. I watched this snippet of interview with in YouTube the Professor Freeman Dyson, and I was kind of surprised that he didn't have PhD. He said, "Oh yeah, I was lucky, yeah, that I didn't have to go through it. I couldn't do it. PhD, oh, that's hardcore, right? Oh my goodness, I couldn't do it. All right, I admire people who did it though, but yeah, Professor Dyson, he was kind of critical of PhD system. Okay, so no system is perfect. Okay, yeah, we can do better. Okay, but so additive set theory. Okay, I learned about it because I looked it up after he passed away in the news. I looked up his biography and there was something like Dyson transformation. Kind of sounds fancy, so I clicked on it, and it deals with additive set theory. Okay, and additive set theory have some application in Goldbox conjecture, and that's I clicked that, and that's how we kind of got here. All right. So okay. Okay. 2 plus 1, 2 plus 2, 2 plus 3. So mm, okay. We don't want any redundancy. Okay. So how about this? Mm, to make the calculation easier. All right. Distribution. Okay. So okay. Okay. So I was wrong. Okay. It seems it's a little bit complex because when you add two sets, there can be some redundancy. Okay, so but we can think about maximum. Okay, the maximum when there is no intersection, no redundancy. Yeah, 2 times 3. Okay, so and if you allow redundancy, then it's always the case. Okay, okay, okay. So so if you have x plus y, cardinal letter is less than or equal to so it's kind of like triangular um, inequality a little bit. Yeah. Okay. Oh boy. But when y is a singleton, then you can prove that let's prove it. All right. We prove this. Singleton. Okay. Set of just one number. Then yeah. Okay. So how do we prove this? Maybe mathematical induction. Varying the number of cardinality of x, I think. I'd rather not use induction, but probably it's easy way to prove it. Very mechanical process. Let's not use induction, okay? We use something else. All right. Okay. this is gonna be very short proof. Okay, this is not thing difficult. All right, so yeah, we were not wrong there. Okay, so our proof is correct. Okay, what we did, and we should give it a name, right? Some theorem, lemma, later. Okay, so okay, ready? Ready or not? Here we go. Proof. Uh, X is union I from 1 to okay, X is not empty set, okay. But because if it's empty set and you add a number, it becomes empty set. Okay? It's like this, okay? Empty set plus 1 is empty set. Because you have nothing to add to. Okay, how interesting, right? It's kind of absorption rule. Okay? How interesting. How interesting. Oh, xi is ith element in this set X. Okay? Now, because Y is a singleton, okay? This is fun. I like this. Set algebra. By definition of set addition, okay, it distributes, right? So okay, this element of this singleton set Y, okay, so okay, so how many of them are there? Yeah, absolute value of X, okay, so therefore yeah, this left hand side, right hand side, okay, QED. We use the definition of this additive set, okay, so that's just how you define addition between two sets, okay? Yeah. Okay, okay, we proved it. Simple enough. You see, proof is such a valuable thing to do. It's very educational because we found something new. Okay, when you prove something, along the way you learn something brand new. Other than the fact that this equation is correct. Yeah, you learn about correctness or incorrectness of your hypothesis, and you learn something else too. You're being very thorough and categorical, very expensive and very thorough, okay, systematic, so you learn something brand new, okay, along the way. That's always the case, all right, in my experience. Huh? Yeah, so proof is very educational, all right, so. Now what? Can we prove this inequality? Let's not do it, okay? Oh yeah, you can prove that because this is the cardinality of multiset, allowing redundancy. Okay, this is cardinality of contracted contraction of multiset. What after you get rid of all the redundancy? Okay, so yeah, it will less than or equal to. Okay, so that's informal proof, conceptual proof. Okay, that's enough. All right, so we're not going to formally prove this. We just verbally proved it. We know why this is the case. Okay, it's about contraction of multiset, transformation from multiset into a set by getting rid of redundancy. So yeah, if there is no redundancy, equal. If there is redundancy, then less than. Okay, so that's the proof. All right. Okay. Let's take 5 minutes break. All right, and I grab my cell phone and take a picture of this, and then we'll move on. We still need to formally prove alpha plus 1 is equal to alpha. Okay, and let's name this lemma. All right, we just call it absorption lemma. Okay, yeah. This we call it set triangular inequality. Okay, so yeah. It kind of like it looks like Cauchy-Schwarz inequality, triangular inequality. Kind of look like that, kinda, right? Yeah. Whatever. How interesting. I like this. This is fun. This is exciting. Windy outside. So what is true for finite set? Is it also true for or theorem that is true for finite set? Is it also true for infinite set? That's a good question to ask, right? For example, this absorption lemma and this triangular inequality is we know it's true for finite set. We proved it, okay? But is it also true for infinite set? That's a good question to ask, right? I do not know yet. We'll find out soon enough, okay? Why? We are not dealing with prime numbers, okay? The rest is so easy, okay? Prime number is like kind of like special forces training, okay? So, yeah. But hey, regular army is not easy, okay? But I've been to special forces training, but regular army was still tough, okay? So it's not easy. Nothing is easy, but after I been through some special forces training because I dropped out after 2 weeks. But to prepare for that, yeah, I did intensely for a month, trained by myself and other special forces candidates and soldiers who passed the selection course. Yeah, we trained together, okay, in Fort Hood, Texas. And after that, yeah, the when I came back, when I dropped out of special forces, went back to regular army, who graciously re-embraced me. Yeah, the PT was very easy. Okay, so for a while, uh, yeah, we yeah been through some difficult times in prime number, right? Gold box conjecture. So it did, the rest of other mathematics is easy. Okay, we can just zip through it. It's more quantitative than qualitative, really. Okay, so look, we disproved head Cantor's continuum hypothesis. Okay, we came up with some counterexample. Okay, so it wasn't very difficult. Okay, of course we have different definition than what he had, but our definition is better than what he had in mind. So yeah, he's cool. Okay, yeah, we learned a lot from him. Just we are correcting him where he erred. That's all. Okay. I think I made some error down there in the proof, okay, because you cannot distribute absolute value, okay, so that's I think where my error was, but I see. Okay, I have to correct myself, okay. We're gonna use. We'll just assume what is true in finite set is also true in infinite set. Let's just assume that, okay. Um, that's a hypothesis, and we're gonna have to prove it separately, but just for now, all right. So I made some error there. Okay, so let's correct it before we forget. Okay, this is where I erred. So let me correct myself. How about you write in red? Correction, back in the days in school, Hey, you got it wrong. Haha. Is it visible? Yeah. Is this correct? Yes. Why? Because it's definition of additive set, right? Yeah. But if this is like 2i, can we do that? I don't know. We got to think about additive set. Okay, so but when it's just number, yeah, then just I mean we don't even need this, all right? You don't need any of this, okay? Oh my goodness. You know what? We'll start over all over, okay? So this is what we want to prove, right? So okay. So let's prove this again, okay? So n is even number union odd number, and they are disjoint. There's no intersection between even number and odd number, right? So right. Okay. You cannot take this two 1/2 out. Okay, why? Because we know if you're gonna take that out, it becomes actually twice of that. So it reverses. When the two cross out, it goes upstairs. Okay. How interesting. That is true for infinite set, but that's not true for finite set. So I guess what's true in finite set can be false in infinite set as well. Okay, all right. Because in finite set, you have from finite set, and you divide by two, uh, this becomes, it just disappears. Okay? Yeah. Because you have single number operator, okay, it's just like plus one, yeah. But when you deal with infinite set, it closes out like this, okay? All right, now, heavy, heavy. Not too heavy. It's just a lot, there's a lot to this. E union O, okay, so you have, okay. Can we distribute this divide by 2 to these two different unions? Yes. Why? By definition of this set algebra, okay, so yeah, you always distribute, okay? Yeah. And can this 2 crawl inside of this union? Yes, yes, yes. It's always distributive, okay? When you are dealing with just singleton, okay? So 2 canceling out, okay, so and okay, now that disjoint, right? So this is absolute value of this guy plus absolute value of this guy. Of course, it's alpha plus alpha, okay? QED. Hola, shoro, okay? Very good. I mean, I kind of like the previous proof more. Why? Because it's kind of fancy, but there are some errors there. So this is a lot simpler proof, and it is correct proof. And then, yeah, okay. How interesting. Satisfied? If you ask me, yes. A little bit disappointed because it's just too easy. I thought you take more intellectual muscle than this, but oh well. We are doing this because gold box conjecture is too difficult. We want to take a break from that. So yeah, easy. If it's easy, no problem. Okay, so that's what break is for, right? Okay, let's take a break. I grab my cell phone and take a picture of this. Okay, and let me write this down. Okay, so January case, just switch 2 into n. Okay, actually, let me, well, 2 to divisor, right? Yeah, change 2 to d, all right? Then everything else is fine. Yeah, that's what I'm gonna write in my notebook. Then it gets more complex, huh? Why? Because it, it's like if this is D. Oh my goodness, it's like we have to do it like DN0 union union DN D minus 1. Okay, oh come on. We'll just do for 2. Okay, it's too mechanical. Okay, we know how to do it. Modulo, categorization of number by divisor, right? What's the remainder? Modulo, arithmetic. Okay, we're not going to do it. Okay, why? Because it's just too easy and too mechanical. That's waste of our time, right? So, okay, yeah. Maybe we'll do it just for fun. We'll do it, okay? Yeah. Just for the heck of it, just for fun. Yeah, we'll prove general case after 5 minutes. Why? Because this is just too easy, right? Yeah, so let's do it. All right. Okay. We take a break and then we prove general case for this. Okay, because it's easy. It's just about notational convention. Okay, let's have some fun with it. All right. All right. Okay. Oh. Where's my pants? Yeah, it's kind of chilly. Whew. Put my socks on and switch to the whiteboard and yeah. Yeah, we proved this absorption lemma. Okay, so very useful lemma. All right. Is it true for infinite set? Yes. Why? I mean, if x is infinite set, yeah, absolute value of x, cardinality. Yeah, by definition of this additive set theory, distribution. Yeah. It's this one is true both for infinite set and finite set. Okay, so just using the definition of set addition. Okay, so okay, all right. Oh. Okay. Do I want to take a picture of this? Okay. Sure. Smile. Good enough. Okay. Let's take a break, shall we? So how are you? You doing good? Yeah. It's too bad all the restaurants are closed. I mean, you cannot dine in. I do that sometimes. Okay, I go to karaoke bar, club sometimes. Sometimes I used to. Okay, nowadays they're closed. So, or takeout only. Unnecessary. Okay. What we want to prove is this. Your left hand side divisor, all right? Right hand side, that's union of I from 0 to d minus 1 dn I. Okay? Well, we use R for reminder. Okay? Yeah, it's modular arithmetic. What is D and R? Is the set of numbers when you divide by D, remainder is R. Okay? So formal definition of D and R, we did this. It became quite complex, right? Wait a minute. Let's finish this, writing this down. Oh. Proof. Okay? So this is N. Okay? Where D and R is formal definition of DNR. Okay, that's it's not Department of Natural Resources. Okay, so it's so formal definition of this is so where formal definition of this is alpha, the unit infinity. Okay, so the count of infinity. Okay, so yeah. We're gonna use a collinear hybrid. Okay, we talked about this before, right? So review. Row algebra. So so row algebra is like this. Okay, like it's remainder. All right. So, for example, if you divide 5 by 3. Remainder is 2. So that's what this rule means, okay? So if you divide I with D, is that equal to this remainder R? Okay, it's cleanly algebra, okay? And I mean cleanly hybrid, meaning if this is true, it returns empty string. So we extract I. If this is false, it returns empty set. So empty set concatenated with something that becomes empty set. Okay? And if it's true, then it returns empty string. And concatenation with something else becomes that something else. Okay? So it's a cleanly hybrid, just like Boolean hybrid, which is Iverson bracket generalization of Kronecker delta. Okay? So, okay? Yeah. It's extraction, okay, of all the numbers when you divide by D. If its remainder is R, then yeah, you take it, otherwise you throw it out. Okay? Yeah. Yeah, it's like ampersand in some computer programming language or mod, right? That operator, remainder operator, that's all it is. Okay, so what I'm saying is congruence, right? Yeah? Yeah, that's what I'm talking about. Okay, so yeah. It's just easier to write it this way, okay? So it's just like ampersand in some computer programming language. Okay, so yeah. Okay? Alright. But this definition is not that important. Why? Because we're not going to use it, right? Now, let's take 5 minutes, alright? So, yeah. I need some vocal rest, so. Okay. Yeah. We'll be right back. Okay. So let's take a break, okay? Back in the days when I was in Madison, Wisconsin, I was reading this book in mathematics library, and then I rented it when I was a student there, and then it was about some algebra. Okay, I tried to understand, but I quite couldn't get it. Okay, so I went to ask a question to a mathematics professor. I was not taking his class, but he kindly and generously helped me understand that very old book in mathematics, like kind of brown-eyed, you know, old book in mathematics library. He helped me understand. Okay, so I was very grateful. For free, I was not taking his class. Okay. I just went to his office. Okay, and later on, I did take his class. It's in combinatorics. Okay, and he told us during the lecture, uh, yeah, I love my job and mathematics really I enjoy doing and I get paid for it. Okay. But do I want to be a mathematics professor one day? Not really. Why? Because I cannot speak for more than 10 or 15 minutes straight. Yeah, I mean, I can open up the floor so that people can ask questions, comments, and just listen to them for 5 minutes. Yeah, it's doable, but yeah, I like my lawyer job, so and I like being a lawyer, so I like doing mathematics as a hobby. Okay, yeah. So Goldbach's conjecture, yeah, we should get back to it at some point, and we should prove it. Okay, we'll get back to it at some point, but I'm not quite ready yet. Why? Because I'm having a lot of fun with this set algebra. Okay, so cardinality theory. Okay, so let me grab some wine and beer because vodka is way too strong. Okay, so it's too hardcore for me and this Sunday morning. So I've been drinking last night. So let's give my esophagus some break. So, there. Okay. Okay. Left hand side. Okay, so yeah, this sets at this joint. There's no intersection. Okay, so Department of Natural Resources. Okay, so D is a constant that has nothing to do with R. D does not depend on R. Okay, that's why you can just plug it in. Okay? Yeah. Wait a minute. Hmm. Yeah, I made a mistake somewhere. Oh. It's not that easy, huh? Yeah, we correct the mistake together. Let's make some example. Okay, so different color. Let me turn off the heater. Okay. Yeah, nowadays I can rhyme very naturally. Okay, like a rapper, hip hop artist, right? Oh, let's change the color and let me turn off the heater. Okay, so N is right. Yeah, we should not use this definition because it's become way too bulky, right? Yeah. So how do we compactly express this? Yeah, with double union. Okay, so nested union. Okay, okay. To generalize this, yeah, so, yeah, we have to restart. I'm sorry, I goofed it up. Alright, so yeah, this definition is cool. It's good to have as a reference, and I'm going to write it down. Then we'll have to erase it. Why? Because wrong way to go. It becomes way too bulky. All right. So. And I'm not even sure if this is correct or not. It should be correct. It's good to know. And let me take a picture of this, alright? Then we'll erase partially. But before that, let's finish this up. In general, okay, n is equal to r from 0 to divisor d minus 1 and I union I from 0 to alpha d times I plus r. Okay? Whew, boy. So n over d, because d does not depend on r or I, it curls inside, so then you have alpha here and times d. Okay, so that's the proof. Okay, okay. That's where to go. This is true too, okay? It just gets too bulky to use, so we're gonna take this approach, alright? Okay, let me take a picture of this. Yeah. Okay. Good, good, good. Oh boy. So so this is n, right? And R is the union variable, outer union. The inner union variable is I. And D does not depend on R or I. So That's why you can curl in and curl in back in again. Okay, so this is like alpha. Okay. Okay. There we go. It's easy. All right. Yeah, it just take time. Because we are not dealing with prime numbers. Okay. So that's the rest is just easy. Okay. Let's take a picture and we take a break. Okay. So let's stop and restart. Okay. I don't want this computer to crash. Okay. So we'll stop and restart. Okay. I'll see you soon.